So the agenda for today is first design rules. Second is ElectroMigration, and third is introduction to S.P.I.C.E. Okay. So design rules, ElectroMigration, and introduction to S.P.I.C.E. So what do you mean by design rules? Let us first define them and let us illustrate them with practical examples. So layman terms, we can say that design rules are rules defined for fabrication of various components on silicon wafer. So design rules are nothing but the rules which are defined for fabrication of various components on silicon wafer. And since there are multiple components on a single layer and also multiple layers on a silicon wafer to ensure no interference or crosstalk between different components, layers. Rules for, this is important, minimum distance of separation rules for minimum distance of separation are defined. Okay, so design rules, these are the rules defined for fabrication of various components on silicon wafer. Since there are multiple components on single layer and there are multiple layers on silicon wafer, to ensure no interference or crosstalk between the different components, rules for minimum distance of separation are defined. So this is like the most precise definition of design rules. So minimum distance of separation are known as design rules. So design rules are nothing but minimum distance of separation values between different layers on a silicon wafer. Now there are two different types of rules. So we can say design rules are classified into two. So first is known as Micron-based rules. And second is Lambda-based, L-A-M-B-D-A, Lambda-based. They're also known as Micron rules or Lambda rules. So Micron-based rules are called as non-scalable rules. And Lambda-based rules are called as scalable rules. So non-scalable means absolute and scalable will also relative. So non-scalable means they are known as absolute rules and scalable means they are relative rules. Okay, so it is important to note that design rules are classified as Micron-based or Lambda-based rules. Micron-based rules are called as non-scalable or also absolute rules, and Lambda-based rules are known as scalable rules or relative rules. Why do we say Lambda-based rules are scalable? We know this when we got introduced to the tool Microwind. We saw that from the scale given on the top left corner of the user interface of Microwind tool, we get the value of lambda, and 2 times the value of lambda is the technology. So we know that the foundry is equal to 2 times lambda, or we can say lambda is foundry divided by 2. Next, since foundry can have different standard values, I cannot say different values, since foundry can have different standard values as 180 nanometers, 120 nanometers, 90 nanometers, 65 nanometers, so on and so forth. Hence, as foundry changes, the value of lambda also changes. Hence, we say that lambda-based rules are called as scalable rules or relative rules. Thus, lambda-based rules are scalable or relative. Okay, so we can give the name here. Okay, and last point about this thing is that in lambda based system, in this system, all minimum dimensions or minimum distances of separation are expressed in terms of multiples of lambda. For example, 2 lambda, 3 lambda, 4 lambda, 6 lambda, 11 lambda, etc. We will try to appreciate in microwind that how all the minimum dimensions or minimum distance of separation are expressed in terms of multiples of lambda. So we will see examples where the minimum width of a layer is 2 lambda, or the minimum distance of separation between two layers is 3 lambda, or that is separation between some layers and some compounds are 6 lambda, etc. We will take classic examples here. Okay, so first we will write down some standard examples of lambda based rules, and we will cross check with the microwind tool whether the rules which we have put down are actually correct. Okay, on the other hand, in case of micron based rules, all the minimum dimensions or distances of separation are expressed in terms of micron, so they are in absolute. Okay, so we can just write one note here. In case of micron based rules, we can only say that all minimum dimensions or minimum distances of separation are expressed in microns, that is micrometers, or sometimes also in mils, MILS. I think 1 mils is equal to 25 microns. 1 mil is mostly it is 25 micrometers. Mostly it is 25 micrometers. Okay, it's only difference. Now let us take standard examples of rules. Okay, so we can say standard rules. So examples of standard rules are the metal and diffusion have minimum width of 3 lambda. The first rule is that metal and diffusion, metal and diffusion. When I say diffusion, it is n plus diffusion and p plus diffusion. So it can be n plus diffusion or it can be p plus diffusion, have minimum width equal to 3 lambda. We'll first write the rules and then we'll verify them. The second standard rule is contacts have dimension 2 lambda by 2 lambda and are surrounded by layers of 1 lambda with surroundings of 1 lambda. Next rule is polysilicon layer has minimum width of 2 lambda. The next rule is polysilicon and contacts have minimum spacing of 3 lambda. And last means there are many more, but this is what we can verify in microwave, is that n well surrounds PMOS transistor by 6 lambda. Okay, so we will see how we can appreciate this in microwave. Okay, so metal has a minimum width of 3 lambda. Let us go to the tool. We have the tool here. So metal should have a minimum width of 3 lambda. So is the UI of microwave visible to you?
Yes, sir.
Yes, sir. Okay. So what we will do, we will take metal 1 and we will just draw a small strip here. Okay. So now I have drawn metal 1. It is having certain width. Now when I say DRC, it is telling me the metal width is less than 3 lambda, which goes to prove that this is the standard rule. That is, metal and diffusion should have a minimum width of 3 lambda. So when I drew a metal layer, then immediately when I said DRC, it said that metal width should be less than 3 lambda. Now what I will do, I will draw a wider metal and I will see that it should not show. You see, so it is not showing. Okay, so if I delete this, if I say DRC, so yes, so the metal width is having a width greater than 3 lambda, so it is not showing any objection, but now it will show an objection. Is it okay? So we have verified the first one. Contacts have dimensions 2 lambda by 2 lambda with surroundings of 1 lambda. See now, we will bring a contact here. We'll push this people here. Let us go to complex contacts, bring a contact and we will say like this. Okay, I will zoom it now. Zoom karenge. Now our rule is telling that contacts have a dimension of 2 lambda by 2 lambda and they are surrounded by a layer of 1 lambda. So what we will do, we will use the measurement tool and we will see what is the distance, what is the height and width of this contact. So I will say measure distance and see here vertical. How much? It is 200. It is 200 nanometer like this. And let us see what is the distance here. Okay, so it is coming 200. Yeah. Okay, so it is coming 4 lambda. It's 2 lambda by 2 lambda. So this is this thing. Now see here, what we have measured is actually wrong. I will tell you why. We have made a statement that contacts have dimension 2 lambda by 2 lambda. So contacts is inside. So we will take this measurement and see, we will do it like this. Okay, so go inside it and see here. How much? It is coming 100 nano. And this is coming 100 nano. So 100 nano is equal to 2 into 50 nano and lambda is equal to 50. See, you can see the scale. In the scale it is written 1 lambda is 50 nanometer. So 100 nanometer of width and 100 nanometer of height indicates it is 2 lambda. So we have justified that contacts have a dimension of 2 lambda by 2 lambda and there are surroundings of 1 lambda each. So this is a layer here. So this is called as layer surrounding. So we will see what is the layer surrounding dimension. So if I do like this here, I am getting 50. So 50 nanometer. 50 nanometer is equal to lambda. So the horizontal layer width is also 50. And if we say the vertical layer width will also be 50. Yeah. So it is proved that contacts have a dimension 2 lambda by 2 lambda. In our foundry, we have lambda as 50 nanometers. So 100 nano by 100 nano is 2 lambda by 2 lambda. And the layer spacing is 50 nanometer, that is 1 lambda. Let us go to another rules. Polysilicon layer has minimum width of 2 lambda. So let us draw polysilicon here and purposefully I will make it very, very thin. Okay. And I will say DRC. See, it did not give a DRC error because it found that it is wider. So what I'll do, I will cut it now. Let us do a DRC. You see here, immediately it is telling the polysilicon width is less than 2 lambda, which goes to prove that if at all in the workspace or on the wafer you are going to etch or fabricate a polysilicon layer, the minimum width should be 2 lambda. Now I draw another polysilicon and I say DRC, it is not showing error. Why? Because it has found that the width of polysilicon layer is larger than 2 lambda. It is vertical, we can make it horizontal also. Okay, like this. Delete this. Okay, same thing. Again, it has given an error because it has found that the width is lesser than 2 lambda. So we have verified this also. Polysilicon and contact should have minimum spacing of 3 lambda. So let us bring a polysilicon and let us bring a contact. So delete everything. Let us bring a polysilicon here. Let us bring a contact also here. Okay, you see here the spacing between poly is less than 3 lambda. So what I did is that I bought a polysilicon layer. I kept a width greater than 3 lambda and I brought a silicon. I bought a contact and we see here the distance between them is 50 lambda, which is 50 nanometers, which is 1 lambda, and the spacing between poly is less than 3 lambda. So we will take another example. We'll drag another polysilicon layer and we will take another contact and we will keep it sufficiently away. So we can clearly see now if I do a DRC, it is giving an error here but not an error here. Why? What is the distance now? We can measure. We can take this scale and we can measure the distance. What is the distance between the contact and polysilicon? It is coming out to be 550 nanometers. 1 lambda is 50 nanometers, so it is 11 lambda. Okay, so distance between the contact and polysilicon is 550 nanometers, and because 50 nanometers is 1 lambda, so I have 11 lambda, so it is not giving any DRC error. And now last, N-well surrounds the PMOS transistor by 6 lambda. How can we demonstrate this? We can actually bring a PMOS transistor in the workspace. Go to MOS generator, bring a PMOS and put it here. Okay. Now what it is written that the N-well surrounds PMOS transistor by 6 lambda. So understand one thing, from this point to this point it is our PMOS and this is the N-well. We have to find out what is the distance between the PMOS transistor and the N-well boundary. This distance and this distance should be 6 lambda. Let us measure. Okay, 300 nanometer. So 300 nanometer is equal to 6 into 50 nanometers. Hence, it is 6 lambda. Let us measure another dimension also. Okay. Again, it is 300 nanometer 6 lambda. We have justified that all the rules which you have written here are actually verified in the layout editor also. We verified everything now. Okay, so because technology keeps on evolving and the foundries go on becoming superior, the lengths go on reducing. That is a micron based rules are no longer used, and all the layout editors or backend tools like Microwind or Cadence, they always conform to lambda based rules. Please be very clear about this thing. I hope that the concept of design layout rules is clear. You can also refer to standard books like Neil Weste. There are pages and pages for rules. Okay, so they are called as SC rules and Moses rules also. So we have so you can Google and find out what they are. At least I can write Moses stands for metal oxide semiconductor implementation service. So it is Moses metal oxide semiconductor implementation service, and SCMOS stands for scalable CMOS rules. SCMOS scalable CMOS rules. Okay, so in the exam when this question is asked about what are design rules, you can give this classification, and you can also give examples of lambda base, and actually on paper you can draw a metal layer. You can say this metal 1 and the width should be minimum 3 lambda. You can show contacts. Inside contacts it is 2 lambda by 2 lambda, and the layer surrounding the 1 lambda. Similarly, you can show another width naming its polysilicon, and you can say minimum width is 2 lambda. Similarly, you can also show a PMOS which is fabricated or embedded inside an N-well, and you can show which are the dimensions with values 6 lambda and 6 lambda. So this will form a complete answer, and you can make a note that micron based rules are no longer used. So we can say they are obsolete. Okay. Yeah. Electromigration is the second topic for the day. So electromigration, I do not know how many of you have heard. Have you heard the term electromigration till now?
No, sir.
No. Fine. So electromigration is actually a combination of two words. It is a combination of two words called as it is electrons plus migration. And all of you know what is migration. We have something called as migratory birds. So in certain seasons when it is too cold in their habitat, they will move to those countries or regions which are a little warmer in order to save their life. So just like migratory birds are birds who migrate or move from one place to another, similarly it many times happens in certain specific metals that electrons actually move from one place to another. That is called as electromigration. So we can, in simple terms, we can say that movement of electrons from one end of a metal to another end under influence of a large potential difference, comma, large electric field is I cannot say it is known as electromigration. It is the cause of electromigration. So movement of electrons from one end of a metal to another end under the influence of large potential difference, comma, large electric field is the cause of electromigration. So please note that although I have said a metal, it is not every metal. It pertains to only those metals which are known for having a granular structure. So aluminum is one such metal which exhibits, or actually it is prone to electromigration effect. So I can say certain metals such as aluminium, that is Al, have a fine grained structure aluminium is thus made up of grains of different sizes. When aluminium wire when aluminium wire carries a current under influence of large electric field E, the high energy electrons bombard on the aluminium grains, pushing them in one direction. What happens next is these grains accumulate at certain spots of the aluminium wire, forming high resistance. Okay, these grains accumulate at certain spots of aluminum wire, forming high resistance. Thus, the flow of current is obstructed, forming hot spots. The above phenomenon is called electromigration. This ultimately degrades wires leading to failure. Okay, and so basically what happens is that when high resistance is formed, the current density is very high. So we can say high current density. Okay, so before also we had studied this. There is something called as MTF, that is mean time to fail. MTF. So MTF is proportional to j raised to minus n e raised to capital T upon kt, where j is the current density, n is a constant, its value is ranging from 1 to 3, q is called as diffusion activation energy, k it's Boltzmann constant, capital T is temperature in degree Kelvin. Okay, and so we can say that a metal wire carrying too much current may succumb to electromigration if the current density J, so we can name it as capital J here, the current density capital J exceeds the safe value. So typically J AL max, that is the current density for aluminium, J AL max is found to be 1 to 2 milliamperes per micrometers. Okay, right. So it is basically the current per unit width. Okay, so current density is defined as current upon the width of the wire. Okay, so we have some statistics here. Usually a metal wire can carry 1.5 milliamperes per micron of its width. That means we can say if I want to conduct 6 milliamperes of current through a wire without damaging it, the wire width should be equal to 6 milliampere upon 1.5 milliampere per micrometer, which has to be equal to 4 micrometer. That means wire width, if it is 4 micrometers, then that wire can carry 6 milliamperes of current without succumbing to electromigration. That is what it means. Okay. Yeah. So third, which we have here, is SPICE. S-P-I-C-E. S.P.I.C.E SPICE. So SPICE is a very powerful language which is used for circuit simulation and also by PhD researchers, and all the simulation tools which you have used till now, like multisim, Proteus, all these tools are able to perform the simulation for your circuit and generate all different kind of waveforms and plot all Bode plots or even frequency responses, because in the background it is using the SPICE language. So basically the heart of tools like multisim and Proteus is a SPICE engine. What does SPICE stand for? SPICE is actually an abbreviation of simulation program with IC emphasis. Okay, so it is simulation program with IC emphasis, S.P.I.C.E. Okay, so SPICE is an abbreviation for simulation program with IC emphasis. Specifically, it has IC emphasis because it is this particular language is meant for actually simulating future devices by changing the different dimensions and seeing how the circuit performs superior compared to the previous one. So SPICE stands for simulation program with IC emphasis. So it is a programming language used for simulating circuits expressed as an interconnection between components, and it can be active, passive components. Third important thing is that we need a SPICE engine to run such programs. We need a SPICE engine to run a SPICE program. SPICE engine is written in Fortran language, that is formula translation. SPICE engine uses nodal analysis to find V, I in a circuit. SPICE is a concurrent language. Language has a rich library of keywords, to represent resistors, inductors, capacitors, diodes, SCRs, BJTs, MOSFETs, dependent plus independent voltage and current sources. Also DC analysis, AC analysis, transient analysis, noise analysis, can be easily performed. And how does it do such a great and wonderful job? Because it uses model library which con contains a complete model, that is behavior of every possible component. So this was just a brief summary about what is SPICE, and from next session we are going to take examples of circuits, that is both simple resistive circuits, and ultimately our aim is to learn how to write a SPICE program to plot the VI characteristics of NMOS transistor, PMOS transistor, CMOS inverter, and if time permits NAND gate also. Okay, so we'll take it from the next session.